demonstrated tonight, right? Project number 1. So you guys know who has signed up. So it will be again about some fun for about 40 minutes. I'll be here and we just do it in this room. Everyone is invited to stay, right? And check it out what your fellow student, co-student is doing. The other thing is next week on Tuesday night after class, show me written up on a printout your paragraph summarizing what you would like to do for your final project. And I decided right then, right there, right? So everyone comes by in a line, says, Bernd, I would like to do this. This is my input, this is my output, this is the algorithm I would like to do. This is the kind of method I use as the basis, and this is my add-on, my improvement of that method. Is that cool? Yes or no? And I will say yes, most likely. But if I think it's way too complicated, I would say stop. I mean, you have to simplify this, okay? Take this out and make it a little bit simpler. Or I will say this is way too simple, you have to make it a little bit more complicated, and I will make some suggestions how to make it a little bit more challenging, okay? So, next Tuesday. And again, I want to be very flexible and very open. If it's something more in the direction of computer animation, fine. If it is more in the direction of computer graphics and realistic rendering of diamonds, fine. If it is more in the direction of hardcore geometric modeling of curves and surfaces, fine. But there has to be some kind of relationship to a visualization of scientific data, right? So as long as that link is there, I'm very open. That is the final project part. Sign up. Some of you guys still have not signed up for project number 1, and I know, right, for the reason. So some probably will still want to demo on Tuesday night next week. So those of you guys who still have to sign up, please raise your hand. Who still has to demo next week? No one? Okay. So I know there are some others in the background who will still have to demo. Okay. Libraries and modules. For the second project, and I hope to talk about it a little bit at the end of the class today, you will have to deal with matrices and matrix inversions and solving linear systems. If you want to write your own Gaussian elimination and pivoting algorithm, etc., and matrix factorization and householder decompositions and QR, whatever, you can do that. Right? If you have already your own library that works well and is very efficient. But I encourage you to just instead use an available module or library that does this for you, since you can rely on that one to be correct, hopefully. Okay, so whatever you have access to on your machine or on your lab, you can use MATLAB packages or linear algebra package modules, whatever. So again, you're welcome to write the matrix code yourself, but it's also fine with me if you just load that in as a library, from a library. Okie doke. And then at the end of the class, maybe I want to talk a little bit about Project 2. If I talk about it or if I don't talk about it, you should begin thinking about Project 2, all right? So at least you should read it, right? After this class tonight, you should read what the sheet says for Project 2, what you should be doing. So you can ask me questions, West Carolina, next Tuesday night, at least, about the expectations for Project 2, what I really would like to see. Then, okay. All right. Or are there some questions already about Project 2? No? Project 2 is very simple. I ask you to implement Shepard's method. I ask you to implement Hardy's method. I ask you to implement the global versions of those and the localized versions of those. I talk about that today. And I ask you to make pictures of the resulting approximations you get. And again, I would like to keep it very simple, make it easy for you. The domain over which you evaluate your approximations can be a cube, right, or a brick. And then all I expect for you to implement in terms of visualization are cutting planes, okay? Cutting planes that go through there in the x direction, the y direction, and the z direction, okay? Very simple. So, or you can, of course, use your raycaster now. If your raycaster is reliable and you have it in place, you could also raycast, of course, these volumes, right, these reconstructions. But again, what I would definitely want to see and need to see is the most basic of visualizers, namely the cut plane, okay? Because I can also see the most by looking at the contours in those cut planes, the color. It tells me the most whether your approximation is good or not, correct or most likely not correct. And that's really Project 2. And now I should talk about it a little bit more and continue there where I stopped last time. Were there any questions about the material I covered? up to last night, Tuesday night? Everything's clear? Okay. So let's jump in there and remind ourselves what Shepard 3 looks like for the three-dimensional case. So I jump in there right away with respect to, with a view on your assignment. Volumetric data, three-dimensional data, temperature readings in this room, temperatures measured at 1,000 locations in this room, and then you reconstructing the field function as a continuum function over the entire room. And then if it's Shepard 3, we also need to estimate or approximate gradients, right? The derivative behavior, how the temperature is actually changing at a particular location for measurement in the x direction, y direction, and z direction, right? Once you have that, then you can feed all the information into Shepard 3, and Shepard 3 will allow you to evaluate on a rectilinear Cartesian grid. Okay, so let's do that. Shepard's method. And I go into S3, which interpolates actually local linear Taylor expansions. Illustration looks like this. So all your data live in XYZ space. And in order to localize everything, Selena, you can put everything into a little bounding box. And so the bounding box is this happy little creature. And so I can only draw the sides. And the sides say this lower left, bottom, and upper right back corners to define this bounding box. And then you have a bunch of other sides somewhere in the interior of the box. Maybe you have 1,000 of those. So the data you have are tuples of the form xi, yi, zi, and only one dependent value, fi, and you have n of those, right? And you want to reconstruct in a continuous way a smooth function over the entire grid. So the first step is for S3. We need to estimate gradients for the sides xi, for sides xi, yi, zi. Okay. And so how do we do that? The basic idea is that we just construct a linear polynomial, a line. Well, the generalization of a line is a plane. For this case, it is actually a linear polynomial in three variables, right? A plus b times x plus c times y plus d times z. That's the linear polynomial we construct. The idea is we construct a local polynomial f. Should I call it f? Should I call it L? I should call it L. A local polynomial L of x, y, z, which takes on the form a plus b times x plus c times y plus d times z. For each side, right? Construct a local polynomial at each side. How do we do that? By considering, well, at least 4 sides, but we consider more than 4 sides. We consider k sides in a local neighborhood. How to choose that k is another problem. I jump in to come to a little bit later. At each side, construct a local polynomial at each side based on nearest neighbors of that site. Nearest doesn't have to be the nearest neighbors, but that's one way of doing it. K nearest neighbors at the site. Okay. What do we get? So if we do this, say we want to construct a local polynomial for this guy, L of x, y, z is what? Then maybe we want to consider 4 a stencil of 4 locally close points. This guy would be in the middle, number 1, number 2, 3, 4. Okay, so that's the one in the middle plus 3 closest neighbors. So we say we consider these 4 to set up a system of equations to determine A, B, C, and D. But in general, just considering 4 will not be good enough. You need a little bit more. How many more? That depends on how local or how localized you would like to be versus how global you would like to be. So this is the indication. We use these k neighbors of I, right? So this would be point I, and these would be the k neighbors. K neighbors of that site I. For example, e.g., the k sites and function values, FCT values considered for site I, that is really xi, y, zi, for site I are, well, there's I locally renumber them, right? I number them from 1 up to k. Every time I have to do that. X1, X2, Y1, Z1, F1. Okay, up to some kth local value. And again, this index here is not the global index, but it's local to that particular site for which I need to estimate something. Up to some last one, xk, yk, zk, and fk. Okay, so these indices here are local indices with respect to this neighborhood of k-1 neighbors surrounding the site in the middle, site k. So then we have k sites and k-dependent function values. We plug them into this equation, and we get an overdetermined system for this equation star, right? We plug all these different values, x1, y1, z1, up to xk, yk, zk, and onto the right-hand side. And this linear polynomial should interpolate the function values here, f1, f2, up to fk, and then it's overdetermined, and then we have to do this least squares thing. So we have a set of equations, overdetermined equation system SUS, which will look like this. So it is 1 times A plus x1 times B plus y1 times C plus z1 times D equals f1, right? That's the first equation. So 1 x1 y1 z1 times unknown vector is just a vector of coefficients A, B, C, D equals the function values at those sites. First one is f1, and now it just goes down to the last site xk, yk, zk, where the function value is fk. Okay, so this is equivalent to writing as at a matrix times coefficient vector C equals right-hand side function value vector f. To solve this guy, as I said, you do this least square step. Least squares computation and you actually solve M transpose, MT, again this superscript T stands for transpose of that matrix, flipping rows and columns of that guy, times M times unknown vector C equals M transpose times function value vector F. That's what you solve. And this is just a 4x4 system. Okay, the product of these two matrices will be a 4x4 matrix. And unless these sites are in a degenerate position, this has a unique solution. And from this, you get the coefficients A, B, C, and D. And the only thing that you need as an estimate is the gradient of this guy. The gradient are just the values B, C, and D. They constitute the gradient, right? So from that, this guy, the gradient, grad L, anywhere independent of location is always BCD because it's a linear polynomial, right? When you differentiate this guy with respect to x, you get B. When you differentiate this with respect to y, you get C, and with differentiation with respect to z, you get C. So that's the gradient. So grad L is everywhere B, C, D. Okay. So now for each site, you also have gradient values. Now for this site, at this point, once you have that, you have actually an xi, yi, zi location, plus you have the fi value, and you have this additional tuple there, b, c, d, right? For each site. So this would be, the BCD tuple for location I, right? And you have these different BCD tuples for every local approximation in a linear fashion. Once you have that information, then you go to S3, and you can just evaluate S3 with that information. Evaluate S3, and for project number 2, looking at project number 2, you just evaluate it on a nice Cartesian grid from 0 to 255, 0, 255, 0, 255, right? So on Cartesian grid, and then you get S3. S3 depends on space, x, y, z, and it is reproducing the function value there is fi. By definition, if the site x, y, the evaluation location x, y, z equals a site x, I, y, I, z, I, or otherwise it is this weighted average of these linear Taylor expansions. So it is sum, the weighted sum 1 over distance I squared of these functions fi of x, y, z, I will say what they are, divided by the sum of all the weights, 1 over di squared. You always want me to put on there that this always goes from 1 to n, I from 1 to n. If otherwise, where these local functions, these locally constructed linear Taylor expansions are defined as follows: fi of x, y, z is the function value there, fi, right? And then you have a local b value there, a local bi, I call it, bi times x minus xi plus the c value from this linear approximation, c times y minus yi plus di times z minus zi. Okay. Okay. That's really all there is to it. Does it make sense so far? Is it okay? Is it cool? What we have to compute, what's given, and what we compute at the very end? Okay. All right. So are there further generalizations of Shepard's method? beyond S3? If I'm asking this question already, then there should be or there are not. Of course there are, right? So you have to read all these journal papers that were written about generalizations of this stuff. And I suggest to read them tonight, as always, right? When I post something like that, or I ask a question, or ask rhetorical questions, or want to stimulate you to do something, then of course you do it. Right? Before I forget this, you have to read the book, of course, before I forget this later. Okay, there is a wonderful book. It's called by my good friend Hamann. And this book is called The Design and Analysis of Spatial Data Structures. I give you this as a snippet now. Why do you need this? Why do you need to worry about that? Okay, I will come back to that later. But you definitely want to take a look at this book, Hamann, The Design and Analysis of Spatial Data Structures, a wonderful book of spatial data structures. And you can get lots of his papers, of course, from his website. And he is currently at has been at the University of Maryland for many decades. U of Maryland, computer science. College Park, University of Maryland, College Park. So, meaning that you also should download his journal papers, and of course his journal papers as well. Okay, he's probably the world's leading authority on all the wonderful, great data structures that we need to accelerate our methods, our search algorithms and query algorithms and update algorithms that we need to do for visualizations of especially very large three-dimensional time-dependent data sets. And he wrote many of the groundbreaking papers in that area. Okay, so many of the later papers are all based on his work, on his seminal work. Okay, so there is another method which is very fundamental, which is called Hardy's method.
Professor?
Yes?
Before we talk about a different method, can I ask, with this Shepard's method,
okay, that's why you guys pay me.
What is the error on Shepard's method compared to using something like Lagrange polynomials?
Okay, first, what's the error? The question should be, what is a good error measure? What are the different types of errors one could define to use to assess the quality of an approximation? And then, how does any of these obtained error values compare to those that one would obtain when one has a different way to approximate data, right? Okay, so how do you do that? First, how do you assess the error? Well, you can really compute the error precisely only if you know the exact function to begin with, analytically, okay? So that's what people have done. They assess the quality of any of these approximation schemes for test functions. And the test functions are, of course, not measurements in this room. They are not skulls, but they are functions f of x, y, z equals x squared plus y squared plus z squared, and many, many more other relevant functions, logarithmic, exponentials, sine functions, for anything, okay? And then they say, okay, for certain classes of test functions, I'm able to reproduce this original analytically defined function within a certain error. Error meaning, well, can be a root mean square error, can be a max error, can be any type of error that makes sense. Usually, root mean square error is a good one. How do you compare the error? Well, for example, if you, for rendering purposes, you evaluate the approximation on a 256 cubed grid, you would just compare the value that you get at any grid point of your approximation from Shepard against the actual value that you know exactly because the original function is defined analytically, x squared plus y squared plus z squared, okay? Then you can compute an exact error value between the analytically defined function, which is defined anywhere, and the approximation at that same site. And then, okay, then you get a bunch of error tables for different types of functions, classes of functions, and for certain types of sampling, distributions of samplings, numbers of samplings, spacing between samplings, you get a certain type of error characteristic, right? Does that make sense?
Yeah, but like if you use Lagrange or Chebyshev polynomials
now
or something.
You use other types of functions. Okay, now you've heard about these other polynomial things. You've heard about Legendre polynomials, you've heard about Chebyshev polynomials, blah, 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 blah. Yes, you can use those too, which relate to the underlying class of basis functions that you use to reproduce, right? And to span your space of linear combinations of certain classes of bases. Yeah. So I didn't present everything in this way, but the types of Shepard approximation is also based on a certain type of basis function, right? I mean, Lagrange polynomials, Legendre polynomials, Chebyshev polynomials. These things are certain types of basis functions which have certain nice properties that lead to best possible approximations for certain classes of functions. That's why they're so famous. And so Shepard's formula, the Shepard apparatus, also has certain basis functions. You would see those if I had expressed everything in the form of the resulting approximation is a sum of certain coefficients times certain functions. And these times certain functions are the basis functions of the Shepard stuff. Shepard bases. And then the other thing is, in the Hardy case, I will really deal with the basis functions to begin with. I will actually talk about the basis functions. Mm-hmm. Okay?
But
now, I have to get the answer. Yes, question 2 was, how do they compare? Okay? Chebyshev polynomials, etc., and other types of polynomials are the best possible basis functions when you reconstruct certain classes of other functions. Why do you do that in the first place? Well, it goes back to approximating certain types of functions in your calculator, in your computer, with other types of functions, using a very short expansion in terms of an expansion, Taylor expansion, Legendre expansion, Chebyshev expansion. Okay, so Chebyshev polynomials are very good to approximate for your numerical calculator 50 years ago by cutting off this infinite series after so and so many terms. That's where these things come from. But all these beautiful properties no longer apply to the general setting of having to reconstruct a function in this room, the temperature function, which is not a function that belongs to any particular beautiful ideal class of mathematically defined functions, right? Chebyshev polynomials and sine functions, cosine functions with changing frequency is all mathematically beautiful, and you can prove that Chebyshev is best for those types of functions, but in your numerical calculator can give you a good number with respect to the 10th decimal point if that's in the context of approximating a skull data set. There is no analytical definition of the skull data set. There's no analytical definition of the temperature in this room. There's no analytical definition of the salinity in the ocean. So you're stuck with assessing the quality of a method by doing computationally empirical assessments, right? Tables, generating error tables, and comparing one method against another method, and assessing the quality of a method based on the type of sampling, how many samples you have, what the distribution is of the sampling, etc., etc. Okay. Next question.
Well, so when you derive the Lagrange or some other kind of polynomial set from the Taylor series, you get a analytical form for the error, which, while it's no use to you if you don't actually know the function. You can't calculate the error. Yeah. It would be nice if you could calculate it exactly, of course. But you know that the error depends on the nth derivative or something like that. Mm-hmm. And if we're modeling some real scientific system, we might have some sort of idea about what that nth derivative is. And in the case of the Shepard method, it's using this more idea of the stuff that's near me is weighted more. So I'm curious if there is an analytic form to the error that would say that, depending on how much the function depends on this local behavior, and somehow quantifies that.
No, there is no analytically a priori assessment of the error. No. But there's another way of making sure that even Shepard and Hardy, that I will talk about, are able to reproduce with zero error certain types of functions. Okay, you can massage the Shepard formula. This is a generalization I didn't talk about. You can massage the Shepard formula and the Hardy formula and all other types of approximation methods in such a way that they reproduce certain types of analytical functions by throwing some additional basis functions in there. Okay, so for example, if all my data points, in the 1D case, if all my data points and function values originate from a line, then an approximation method would be good if it reproduced that line always with 0 error, right? That is a precision set. That is a class of functions that a particular approximation method is able to reproduce with 0 error. Okay? So, for example, this Shepard stuff that I talked about, you can ask the question, okay, this way, when I have Shepard and consider function values and I have gradients, and the gradients are computed in this way, could I guarantee that if my original function was a function f of x by z equals 5 plus 2x plus 3y plus 10z, could I then guarantee that this Shepard would reproduce that function without error at any of my 256 grid points? Yes or no? Answer. And so if you want to reproduce certain types of sine functions, certain types of cosine functions, how do you do that? By just adding some additional basis functions into your expansions, which also have the basis function in there to reproduce certain types of sine, cosine signals, right? So, but at some point you will be able no longer to say that a certain phenomenon in this room is a certain beautiful mathematical ideal. Right? You have to give that up at some point. Does this help? Okay, good. All right, so Hardy's method, 1D. So the setting is, of course, the same. We have x and y, and we have samples irregularly spaced. And that looks like this. So there is a side I, a first side 1, a last side n, and bullets as function values. And we would like to get this, right? So Hardy, the Hardy function, I call it h for Hardy, would be just a function of x, and it's just this function, I from 1 to n, and I'm specific here. I just say this is certain coefficients, unknown coefficients, times something square root of r squared plus bi squared of x. This is the original Hardy method. All right. So I'm writing this in a different way, right? Shepard's method, I said that an estimate is a combination of original stuff with certain weights in front of it. Here I say, well, the estimate at some location x is, well, an expansion. And this expansion has certain coefficients, right? Some numbers times certain basis functions. These are these basis functions. They are the Hardy basis function. And what is what here? We don't know what the C is. We don't know what the R is. And I should say again what the D is. Where di squared is merely the square of the distance between an arbitrary x and a side xi, so it's just x minus xi squared, right? The other thing is r squared. This will become a tricky parameter. R squared is just some positive number. Positive number, and that's very tricky to choose that. It's easy for me to say that. And then the CIs are the unknown coefficients in this expansion. CIs are real valued coefficients. These are the unknowns, unknown coefficients. Coming back to your question, okay, now you shouldn't start me on these questions, okay, because this is approximation, right? So if I had a line to begin with, but then my sensors just sample this line somehow, right? I sample here, I sample there, I have some samples here and a sample there, okay? In this case, my sensors, my measurement devices, will give me these points. Of course, my reconstruction should be able to reconstruct this line exactly. Huh? So you can say this approximation method is precise with respect to all linear functions, regardless of how many samples I have, regardless of what the spacing is between the samples. Right? So you say, well, I want another type of quality. If my samples were to come from this type of a creature, right, and I have samples like these, okay, then regardless of the number of samples I have, regardless of the spacing between samples, when they come from a sine function, I would like to be able to reconstruct that sine function with zero error. Right? There are certain types of methods that do that. And so there are these different types of classes of approximation methods for the different types of applications, functions, and so on. You get the idea how this works? Okay. And again, you can force this type of behavior to be linearly precise, to be sine function precise, by adding to these expansions the types of basis function. Here the basis function is just x. Here the basis function would be sine x. Right? And if you want to you get a coefficient for that that you reproduce in the case that your original samples come from such an ideal world. Okay. Enough of that. Because this would be pretty bad, right? If my samples came from this line and I had a reconstruction that looks like this, I don't like that, right? Huh? But Shepard might do that. Shepard will do that if you don't force the gradient. Huh? I talked about that we have flat spots, right? Shepard will have, without the fix of the gradient input, will give you flat spots if you do this. Right?
Just to add or question, it seems like Shepard's methods are all linear, not necessarily the sine function or the cosine function. So you can have a category in of itself.
Yeah. All right. So this is a different setting, and we need to set up a linear system for those unknown coefficients. Can we set up that system? And where is the system? Where are the equations defining that system? Need to set up a system of equations to obtain the CIs, obtain the unknown CI values, the CIs. And again, I will do that only for simplicity reasons for the 1D case, because the 2D case and 3D case and ND case then follow automatically. What are the conditions? What are the conditions? The conditions are that whenever I evaluate capital H at location 1, I would like that function to reproduce function value 1. Whenever I evaluate capital H at xi, I want it to return fi. And at the last point, xn, it should reproduce fn. Those are the conditions. I just write this down as conditions, 5 conditions. Right? So, what are the interpolation conditions for H? Interpolation conditions. Conditions for H. For H of x, in general, we have n of those. So I just have to evaluate H at the first location. H at x1, well, equals what? I plug x1 into that formula. That is just the sum I from 1 to n, unknown coefficient ci times the square root stuff, square root r squared plus di of x1 squared. And that should reproduce the value there that I'm given, which is the value f1. Okay, all the other equations look the same, and the last equation in particular is evaluating h at xn. So last step would be evaluating this Hardy function at the last point, last side, and I get a sum from 1 to n unknown coefficient ci times square root of r squared plus di of xn squared. And that must reproduce the last observation, the last measurement, fn. So these are my happy n equations. N equations. N equations for the n unknowns, C1 up to Cn, right? Should work. We actually should prove that that works, right? But that goes back to linear algebra. You have to prove the linear independence of those basis functions, right? So you can do that at home. All right, so we can write this in matrix form. Written in matrix form, and that's where my comment came from, that you can use a linear algebra package to solve this matrix problem that comes up now. Written in matrix form. Matrix form. Okay, matrix form. Well, I always start writing that big matrix first. So the first equation, the unknown vector is a vector of the CIs, right? So surely my unknown vector here is my C1 up to Cn. I know that. And I know that on the right-hand side, I would like to interpolate the function values f1 up to fn. And now I just have to compute the elements of that matrix, and they are captured in this sum. So I just have to do it for first side. So the sum multiplies all the coefficient vector with these basis functions. So the basis functions here go in the first row to multiply the vector. So now I plug in there I is 1, I is 2, I is n, right? Okay, so the first expression here would be square root of r squared plus d1 squared x1, right? R squared plus d1 squared of x1. And I just make dot, dot, dot. The last entry here, upper right corner, matrix entry would be evaluating the sum for n. So it is dn at x1. So it is r squared plus d1 squared at xn. All right, now I go straight to the last row. In this matrix, last row is evaluating the same sum for the last side xn. So I start with d1 at xn. So this one becomes square root of r squared plus d1 squared at xn. And then the last entry, lower right, is square root of r squared plus dn squared at xn. But that's the matrix. Okay. That's all we need to do. And then there are some observations. We have to think about that a little bit. Whether this is good, whether this is bad, easily solved, not so easily solved, computationally expensive, computationally or numerically stable or unstable, etc., etc. It's expensive to solve the system. That depends on what number? That depends on n. Okay. Is this a big matrix or is this a small matrix? That depends on n. Is this matrix of any particular type? Like, is it sparse? Like, is it a diagonal matrix? Like, is it a block structured matrix? Like, is it a diagonally dominant matrix? Like, is it a symmetric matrix? Any of these nice, beautiful properties?
Well, for along the diagonal, it's going to be square root of r squared. Because
everywhere, right?
D1.
Everywhere, right. So d1 to x1 this is the distance of location point 1 to itself is 0, right? So this is 0. So this whole thing just becomes square root of r squared, which is r. And so the entire diagonal, this also is the last, evaluation location is side n. And so side n has distance 0 to itself. So this also, right? 0, the distance is also square root of r squared, which is r. So this entire diagonal is square root of r squared is r. All right. That's the only nice thing that you can see about this matrix. Otherwise, there's nothing nice about it. Why? Because all these points are in arbitrary location. Right? If these sites were somehow regularly spaced and beautifully spaced, and there was some pattern to it, then there would be a pattern that would be replicated in the matrix. But in the general setting, there's nothing nice to this matrix. It's full-blown. There are no zeros in it. It is not diagonally dominant, unless r is chosen in some magic way. It's not symmetric, and therefore this whole thing will be very expensive and also numerically unstable if this r square isn't properly chosen. Okay, and you will run into some problems when you deal with this. So observations are just a node. Okay, a node. And I think Professor Bai will talk about those types of things in his class in numerical linear algebra, how to deal with different classes, different types of matrices, and how to factorize them, all of that. Node. So this is matrix notation. This is just matrix M times unknown vector C equals function vector F, right? And then I can talk about M. M is not a nice matrix. Matrix of any particular type that would ensure numerically stable and computationally efficient inversion. That would ensure numerically stable or computationally efficient inversion, or computationally efficient inversion or factorization. So this makes us very sad, right? And so therefore, how expensive is it to compute the inverse of such a full-blown general matrix? If we talk about the numbers of multiplications and divisions in the Gauss algorithm, right? Gaussian elimination. Remember that, how expensive that is? N cubed, yes. Generally order n cubed cost, and that is the multiplication cost for inversion. So if you have 1,000,000 samples, 1,000,000 is a small number, right? But 1,000,000 cubed is a big number, even for a GPU. So actually 1,000,000,000 samples isn't a lot today, right? But 1,000,000,000 cubed is really a lot. So it's not nice. All right. The other observation that Jennifer made is that the diagonal there is square root of r squared. Diagonal of M. Now of M is square root r squared throughout square root r squared. So, and you remember this from linear algebra, matrices that are at least diagonally dominant are numerically good or better than those where the values in the main diagonal are very small relative to the rest of the stuff, right, in a column or in a row. Remember that from numerical algebra somewhat. So therefore, this r square value should be chosen in such a way that you can at least ensure diagonal dominance of such a matrix, okay? And that means that this R-square thing has to be chosen dependent on the spacing and the sides, right? Because the other elements depend on the actual geometry, the location. So this means should choose, and this is a hint for the second project, right? Should choose R squared such that ST such that M is or is nearly diagonally dominant the matrix, diagonally dominant. And look that up in your linear algebra book what that meant. Diagonally dominant. Now I can go very quickly to the three-dimensional case because it's all the same. One second. It's all the same, 1D, 2D, 3D, except that the meaning of x now becomes a tuple of x by z. And the other issue is, well, we need to worry about the speed of things here, right? Whether it's Shepard, and particularly when it's Hardy, this stuff becomes expensive and we have to deal with that. And that's where I go back to Hamann and Summit and talk about efficiency improvements. Sure.
Are all the subscripts right in that matrix for D?
Mm-hmm. Right. These are subscripts.
The upper right.
In the upper right?
D1.
N.
D1. Oh, this is distance n, right? To x1?
Yeah.
To x1, yeah. D1, x1, 1 and n. 1 to xn, n to n. Yeah, you got me. Mistake. Upper right corner entry correction has to be distance n to side x1. Should.
Is there any discussion on the step size of x? Or are we going to disregard this method anyway, and so you won't get into that?
The step size?
We're doing x minus x1. D squared is equal to x minus x1.
Right.
So what's the size of x?
X is the arbitrary evaluation site. So this is the meaning of x. So I have samples. These are the sample locations. My x1, my x2, my x5 in this case. And now I want to render this thing with a high-resolution polyline. Right? So I want to actually produce a polyline that looks like that. This is 1,000, so I need to evaluate this thing at all these gazillion x values. That's the meaning of x. Okay, so for any of these arbitrary x locations, I need this distance between this x and the xi's. Those are the distances. The distance value squared between the location that I evaluate and the side. Make sense?
It does make sense.
Okay. All right. Are there any other questions about the 1D case? Because in the 1D I jumped straight to 3D, which is the same. And then I talk about spatial data structures, at least some of those that we all should code up tonight just for fun. Am I kidding? I think sometimes you cannot tell whether I'm kidding or not, right? That's good. So, let's see, 3D case. 3D, Hardy. What has changed? The picture has changed only. Only the picture changes, right? Now, my sites are again living in a bounding box because I ask you to only make cut plane visualizations, which are done very well or easily when I have a bounding box, which is maybe even a unit cube to make it even simpler. And so you put it down in a cube, right? Okay. Here you have your original locations. Bam, 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 bam. So a bunch of sites. No gradients, okay? I'm not talking about gradients here. We just feed the Hardy machinery just the raw numbers, the raw data, the Fi values. I'm not talking about the gradients yet. So again, you have a bunch of sites. It's an xi, yi, zi, fi. And you solve Hardy. Hardy in the 3D case is h of x by z, which is the same thing. It's an expansion. It's just one sum, which consists of n terms of certain coefficients, ci, multiplying certain basis functions. And the basis functions are these functions. It's still just one number, a positive number, r squared, plus, and now the notion of distance is distance in three-dimensional space between a location and a site, and no longer just a line distance. So it's a distance I squared of x, y, z. Right? So the only thing that changes is that we are dealing with x by z instead of just an x. And the conditions, interpolation conditions, and I don't write the matrix down, interpolation conditions. In this case are when I evaluate h at the site xj, yj, zj, then I should reproduce that value there. It should be the function value there, fj, and that should be the result from evaluating that sum. That should be the result when evaluating that sum from 1 to n, coefficient ci times square root of r squared plus di squared to an xj, yj, zj. Right? And this must hold for all nf values, j from 1 to n. Right? And then you can write this in this beautiful matrix form like the matrix over there. Right? These are these n equations. You can spell them out. You can write them as a matrix, and then you're in the same setting. Otherwise, the same, formally the same as the 1D case. Formally, just like 1D case. Except that the notion of an x is now a tuple x by z. Right. And so the 2D case I've left out completely because it lies in between, right? So it's boring. All right. Okay, I should say a little bit about nomenclature. On the assignment, I will ask you to compute what is called the Hardy method, the Hardy multiquadric method, and there's another one that's called the Hardy reciprocal multiquadric method. So I have to tell you what that is. There are two basic Hardy methods, two basic Hardy methods. Hardy methods, and one is called Roman 1 Hardy's multiquadric. Hardy's multiquadric. Why is something called a multiquadric? Where does this nomenclature come from? Multiquadric. Quadric, and then there is something that is called 2 Hardy's reciprocal multiquadric. Reciprocal multiquadric. Okay, I have to give you the definition of both. So this first one, h of x, I just write this now as a boldface x, whether it's dimensionless, it can be any dimension. H of x is some coefficient ci times, okay, there is this r squared thing, r squared plus di squared of x to some power, and this power was 1/2. That is the square root that I used over there. So I just talked about the multiquadric. And then this reciprocal multiquadric uses a different exponent. It uses minus 1/2. It uses coefficients multiplying different basis functions, and now the basis functions are r squared plus di squared of x to the power of minus 1/2. Okay, so these exponents explain the nomenclature. So one is the multiquadric basis function, the other one is the reciprocal multiquadric basis function. There are many, many other versions of it. Again, right? The list goes on and on. But I'm talking about those for, this is important for project 2. Now we need to talk about acceleration and speeding this stuff up, right? Mr. Shashkov? Do you know how to do that? How to speed it up? I gave the n readings, right? From sensors that are measuring the temperature in this room all the time at 1,000 hertz per second at 1,000 locations, right? And you need to always do this n-cubed algorithm over there to reproduce a continuum, right? For all these time steps to make a smooth movie. But it takes so long. So how can we speed it up?
Use less data.
To use less data? No, you have 1 million data readings. You want to use them all, right? You use what you have, no? Why do you record 1 million data when you don't want to use them all?
It's on your area of interest. So if your area of interest is that corner, these corners might matter less.
All right. Those are already higher level, right? Thoughts and ideas. I mean, if I just want to make a picture of high quality close to the door because I want to understand maybe how the temperature in the door area is fluctuating over time, yeah, I'd use an adaptive subset of the samples, right, for the application, yeah. The other thing is I always use all n samples, right, for Shepard and for Hardy. I always use all the n data that I have. Do I have to do that for an atomic step of computation, or can I use maybe less? Yes, I can use less maybe, right? I can use...
Choose a k nearest.
I can use k and n, the k and n graph, right? Choose the k nearest ones. That's why we have computational geometry, and that's why we have all the beautiful work by Hamann and Samit, where he tells us how to do very effective and efficient k nearest neighbor searches based on certain spatial data structures, like KD trees, like octress, like triangulations, like tessellations, like Volno diagrams, like a bunch of stuff. Some of that stuff is more easily programmed, some of that stuff is much more difficult to program. Some of that stuff is better for certain applications and less appropriate for other applications. But there's no way around it. If you want to accelerate this, and you don't want to go into parallelization, which is another way, of course, to do it, is you need to use very clever software. And one part of the clever software is a clever data structure, right? And localization. And the localization part also requires intelligence. You need to make sure that if I localize this thing, I want to localize it just in a proper way. I do not want to make things too local, and I don't want to make them global, so I want to do something in between, right? So choosing K. Acceleration, spatial data structures, and maybe we can all program it tonight together. K nearest neighbors. Well, we can localize it, right? Why is it still expensive? I mean, if I do this computation, this Hardy stuff, for example, just using the 10 closest ones, if I need a value here, right, and this is not an original site, then I need to find the 10 closest sites where I have a temperature reading to get a number here, right? All right. I use only 10. If I only use 10, then that ugly matrix over there is of 10 by 10 in size, so I can do that quickly, right? But which operation is then expensive? I need to find the 10 closest ones. Okay, so I have not solved the problem. I go from one problem to the next problem, right? Namely, to be able to finding the k closest ones efficiently. That's where these quad trees and these octrees come in, which are the most popular and the most easily programmed structures. So localize, and I become very specific now with an eye on your project number 2 to really help you, right? There's much more to this whole story. But I just focus on project number 2 and say localize Shepard and Hardy by only considering the k closest neighbors when computing an estimate for a location x, by considering only the k nearest neighbors, nearest KNN nearest neighbors, the k nearest neighbors of an evaluation location, well, I can say x by z in 3 space wide project 2 of an evaluation x by z. That's the magic, okay? And then we are happy because that should speed things up. But then we think about it, and after some time we are not so happy because we have introduced a new problem, this k and n problem, right? You have to do that. So we have a new problem to solve. New problem. We need a good spatial data structure that allows us to identify the k nearest neighbors quickly. Need good, and there are entire books about that, of course. Need good data structure to determine the k and n's quickly, to determine the k nearest neighbors. I will just call them the k and n's, okay? K and n's, k nearest neighbors. Okay, I just call these guys k and n's, k nearest neighbors, okay? K and n's, to determine the k and n's quickly. Okay. Problem, or the illustration of the problem, is this. Problem, 2D case. I'm just looking down from above into the xy plane, and I have my k being, I don't know, 6, and the point itself counts as a neighbor to itself, so that's neighbor 1. I myself am my own neighbor, right? So that's 1. Then I have 5 other ones around me. Different people have different conventions for that. But so I have sides, 6, right, these are my original sides. And now comes the evaluation step. Now I want to evaluate. This guy is the evaluation location that I called it, right? Evaluation location there. Evaluation location. And so I want to evaluate this thing for rendering, of course, on a nice mesh, right? And I have all my pixels, so whatever I use, and I need a value there. So this is my evaluation location. And then I need to find quickly, because I do this right very quickly, and I need my k closest sites. These are the original sites. Right, I just call them sites. That's the given stuff. That's the locations of the original measurements. So the result have to be 1, 2, 3, 4, 5, 6. Right. So these double circles are the ones which are indeed the 6 closest to star location. Right. That's it. That's what I want to get. Now my eye does this very quickly because my eye can see it, right? Computer cannot see that. Computer has to do it. So these guys are the KNNs that I want. KNNs, the double circles. KNNs of the evaluation location and the single circles and also the double circles are the original size. All right. I do not know whether I asked you on the project number 2 page to actually develop a spatial data structure or not. If I don't ask you, you should do it anyway for special credit and because you need these spatial data structures anyway. Who could live without them? Right? No. Am I kidding or not? Of course you need the spatial data structures. You need a working octree. Sooner or later, for your research careers, you need a working octree. Okay? If you don't have that working octree, you will have nightmares for the rest of your life. So find the best possible working octree data structures for 3D point sets. Okay? To build it, to eliminate things from it, to insert things into it, and to query the data structure efficiently, and to also handle it out of core, because even the octrees can get very large when the data set is very large. Right? You need a good one. So, but we are in the 2D case. In the 2D case, these octrees are actually called quadtrees, right? So, structures, data structures. To do this, and quadtrees, trees for 2D, and then they become octrees. I don't want to draw those octrees in 3D. So what's the general result of such an analysis? I give you the result that comes out that your program should produce when building the hierarchical structure. And then I give you the tree. It's a tree structure. And I say, let's call this a parameter m. Okay, m should be m smaller equal 4. Okay, that's a condition, m smaller equal 4. The semantics is that in any quadrilateral, any quad, I would like to have no more than 4 points or sides. Okay, means no more than 4 points per quadrilateral. Okay, so therefore I can now, if this is the result, now I want to go one level deeper. Okay, so this is the result. So if this is a result of constructing something when none of these quads is more than 4 in there, then one valid point set, original point set, could look like this, right? Okay, right? So what was the algorithm that constructed this? The algorithm starts with a bounding box, right? Lower left corner is a side. This one was a side, so this is a bounding box. So it doesn't have to be a square. It can be a rectangle. And then you bisect the edges, okay? You say, I have 50 points, so therefore condition is violated, split. And split in a quad fashion means if my root is parent Q, then after the first split, 1 becomes 4 or produces 4 children, right? 1, 2, 3, 4 on that next level. So I call this quad 1, quad 2, quad 3, and quad 4. Right? Those are the children of the root. And 1, 2, 3, 4. Quad 1, quad 2, quad 3, quad 4. All right? Quad 1 is done because it only has 2 in it. This is done. This is done. Has 4 limit. that this guy has too many in it. I need to split it further. Okay, so then 4 gets split further. I don't want to put the names down, but I just say it goes like that. It has 4 children, right? Child 1, child 2, child 3, child 4 locally. But then I see in this particular child, quadrilateral, I have too many, so I have to go bisect the edges again. All right, so which one is this? This was quad 1, quad 2, so this would be the second guy. They're saying this one again splits into 4 children. And then it's done, okay? And then I have the leaves of the tree. This is the leaf, this is the leaf, this is the leaf, and here I have the leaves. And these were leaves. Done.
When you split it, do you always create new quadrilaterals that are of equal area?
Yes. And again, there's entire lists of papers on just how to split, how to subdivide. Right? This is this brutal one. Left boundary, right boundary, take the midpoint. Right? Bottom value, top value, take the middle line. And then you can also consider the distribution of points to kind of like optimally have this hierarchy. And then depending on the distribution of the points and depending on the type of tree you would like to produce a very well-balanced tree, you have different strategies, okay? So this might not be the best tree. Maybe you want to have a certain depth and all of that. So the most primitive one always takes the midpoint. Blah, blah, blah. And if you think about this, just do that. So that's that. All right. You have a side set coming in, the measurement readings in this room. You can easily construct this, right? You can do that. That's relatively easy. You can also think of a tree structure. You have all programmed your trees before. You know that that's a nightmare with the pointers and the traversal and the insertion and deletion and update and whatnot, because this gets updated, right? You have to change this. When points come in, points go out, right? This is a dynamic structure. It has to be a dynamic structure. It's not fixed. And so now you have to use it. What is the usage of the structure? The usage is for this purpose, right? The usage is, okay, these are my sides over the xy plane. And now I do my Shepard or my Hardy thing, and I want to produce a nice picture, right? In order to do that, sooner or later, I have to evaluate at this particular pixel location and evaluate there, right? I have to evaluate there. In order to do that, I said I need to consider 6 values, right? So then the issue is, if I'm at this location and I need to evaluate and I want to use 6 closest ones, how does this particular structure and this tree representation of that structure allow me to find those 6 closest ones quickly? No? That's the next question you have to ask yourself, right? If I have to evaluate here, that's the evaluation location, and I have this structure in place, I can easily find out where this location lives. It lives in this particular quad, which in the tree lives somewhere. And for this location, I have to consider this guy. I have to consider this guy, obviously, this guy. And how many did I say? It's considered itself. It's number 4 and 5 and 6. 5 and 6 are probably these guys, right? How do I get that quickly? And that's the question, right? That's why you have to read Hamann Summit. Because that's not obvious, okay? That's not easy, how to traverse a tree with that query, right? Given an arbitrary location now, right? That's the thing. An arbitrary location in this hierarchical tree structure, which are the 6 closest ones to this arbitrary location. Right? Okay. That's one thing that accelerates this, and I will hit on 2 more just to give you the idea. Then we look at more projects to have some fun. At least I can have some fun. So there's something called natural neighbors. Natural neighbors. And that is related to Borno diagrams. Much more complicated, but in a sense more natural. Leads to the concept of natural neighbors. Natural neighbors. How does it work? I just give you the general or just a specific instance of an example in 2D. So if I give you a certain arrangement of sites like this, then the Warner diagram of this site set would look like this. Okay, that's the Warner diagram of that set of points. Right, so these are my sites. Where would I want to evaluate a scalar data interpolation? A scalar data interpolation I probably would want to evaluate over a bounding box that goes around my sites that I have measured. Right, so inside this box I would like to approximate using Shepard or Hardy, and then the general question will be, if I'm at this particular location, right, this particular line, this particular scan line, this particular column, I need to figure out how to get a value there. And the question is, well, what are the natural neighbors of this evaluation location? The natural neighbors of this evaluation location are the point, the site that is in the same tile where this guy is, and the sites that are the natural neighbors of this tile. Okay, so in this particular case, I would use this guy, this guy, this guy, this guy, that guy, and that guy. Okay. That means whenever I have a pixel or an evaluation location inside this is a tile, called a tile, then I would always use these 7. Okay. So the number of double circles I would consider changes, right? Because this diagram is not generally so regular. So, but this is much more complicated a structure. You can think about that, right? That this structure is much harder to construct and much harder to traverse and research in than this. Is there another structure that I want to talk about? Warner diagrams, natural neighbors. Well, the most brutal one, of course, is to do it just in the naive way. If I evaluate a location, at a location of all the points, determine the k closest ones, right? But in the naive way programmed, you would say for all the points, compute points distance to evaluation location, and then keep track of which is the closest, second closest, third closest. But that is expensive, because that would be order of number of evaluation sites times number of sites you have, right? So very expensive. Can't do that in a naive way. Okay. And the other trick is, of course, parallelization, right? You do it in a multi-threaded way. You use all the threads, all the cores you have available, right? Or you just cut your domain over which you want to rasterize or raycast into octants, right? Take this room and just cut it into 8 octants and have one core dedicated to each octant. If you have several thousand cores, just cut the room into many thousand little rooms, right? Okay. All right. I don't even have to talk about Project 2 because I think I told you everything about Project 2. So next time I can talk about it more. So next time would be good if you come with your questions, okay? At the beginning of next lecture, bring your question that you have about program number 2, assignment number 2, and ask me, okay? And then we will have a dialogue about it. All right, so I will come back in 2 minutes, okay? Thank you.